I'm Haruki Morimoto from Kyoto Institute of Technology. Today I'll talk about numerical simulation effect of non-Newtonian properties on the motion of a single particle cell and the blood rheology. First, I will explain the introduction. Rheology is the study of the deformation and flow of matter. Suspension is a dispersion system in which particles are dispersed in a liquid. This is involved in many of the industrial products and medical fields around us. For example, the blood, ink, cosmetic, medicine, and medicines. In this, we focus on blood. Blood is suspension of tangible components such as red blood cells in liquid components such as plasma. Hereinafter, red blood cells refers as to RBC. Among the tangible components, RBC constitutes a high proportion. Therefore, we think it is important to understand the rheology of RBC suspension. RBC has deformability and aggregation capacity. Look at this graph. At low shear rate, it shows aggregation capacity, and the relative viscosity of blood is high. On the other hand, at high shear rate, it shows deformability, and the relative viscosity is low. Much research has been done on this, and RBC has several different motion modes. These characteristics affect the rheological properties. Therefore, further research is needed on the motion mode. It is so that the motion mode of RBC contributes to the non-Newtonian properties of the blood. Therefore, we investigated the influence of motion mode RBC on the rheological properties on blood. In previous studies, Knight et al. Suggest that RBC undergo tinctuating, tumbling, and flow alignment motions in two-dimensional shear flow, depending on capillary number. Tinctuating is a motion in which RBC shows orientation more. RBC suggests that changing in blood viscosity. Tinctuating is the motion in which RBC is oriented in the direction of flow, with only the membrane rotating. And tumbling is a motion in which RBC shows rotational motion of the RBC itself. And Gigliotti et al. Suggests that these changes in motion mode of RBC suggest that changes in blood viscosity. Therefore, studies on RBC motion mode have been conducted using capillary numbers. However, we focused on the internal and external viscosity ratio. Internal and external viscosity ratio is expressed by this equation, using the fluid viscosity inside the membrane and the fluid viscosity outside. At low internal and external viscosity ratio, the motion is referred to as tinctuating motion. The inclination angle was used as the evaluation index of tinctuating motion. The inclination angle is the angle at which the long axis of the RBC is tilted from the axis of the channel center. At a high internal and external viscosity ratio, RBC shows tumbling motion. The tumbling frequency was used as an evaluation index of tumbling motion. The tumbling frequency is time taken for one rotating of the RBC. In previous research, Nakasui and Fukui suggest that RBC undergo tinctuating and tumbling motions. This figure shows relationship between viscosity ratio and intrinsic viscosity. RBC shows tinctuating motion when lambda equals 3 and 5, between 3 and 5. RBC shows tumbling motion where lambda is between 5.5 and 7. Then the critical internal and external viscosity ratio is a viscosity ratio that is point of change in this motion, this black line. Internal and external viscosity ratio of human blood is said to be about 4. In general, plasma is often treated as Newtonian. However, Mura et al. Suggests that plasma exhibits non-Newtonian behavior due to its protein content. Our research objective is to investigate the rheological properties of RBC suspensions. Therefore, we investigated the effect of non-Newtonian property of plasma on the critical internal and external viscosity ratio, which is the change of point of motion. I will present this content. The creation model and the main parameters are described. Shear flow was used for the analysis because of the ease of handling the rotation of the object. We simulated a shear flow with moving up and lower force, placing RBC in center of the channel. The particle Reynolds number is set to 0.1. Parameters were selected with reference to previous studies. And power law index was set to 0.9, 1, and 1.1. I will discuss the governing equation. We use the regularized Cauchy-Boltzmann method as governing equation for the fluid. Also, we use the spring network model as a governing equation for particle. In the spring network model, the energy is calculated from expansion and contraction, and bending, and area constraint respectively. These three energies calculate the restoring force of the spring by the principle of virtual work. Then the equation of motion is solved using restoring and fluid force. Next, I will discuss power law index model. In this study, power law index model was used to express non-Newtonian properties of plasma. One of the advantages of power law index model is its analytical ease of use. When the power law index equals to 1, the fluid is Newtonian fluid. When n is less than 1, it is Shear-Schilling fluid. And when n is greater than 1, it is Shear-Schilling fluid. Next, I will explain virtual flux method. We used virtual flux method to calculate the interface between fluid and soft particle on Cartesian grid. Virtual flux method has these advantages. Any shape of object can be expressed in Cartesian grids. The physical quantities around objects are accurately calculated. Simple algorithms. Computational efficiency better than immerse boundary methods. The physical quantities on the virtual boundary use no-slip condition for velocity and the Neumann boundary condition for pressure. And virtual physical quantities are calculated using this equation. Next, I will explain parallel computing. In this study, OpenMP was used for parallel computing. The specification of the PC as described here. The efficiency of parallel computing was evaluated. The speed-up ratio tends to increase with increased number of threads. And the speed-up ratio did not change much when the number of threads can 8 and 16. It is considered that the increase in the number of threads increased over the overhead of the parallel computation of the spring network model and VFM. Next, I will explain the results of our research and consider them. First, we investigated the effect of the internal and external viscosity ratio on the intrinsic viscosity with Newtonian plasma. Here, we fix power law index to 1. Next, we investigated the effect of internal and external viscosity ratio in the intrinsic viscosity with non-Newtonian plasma. Here, we fix power law index to 0.9 and 1.1. First, we investigated the Newton plasma. Here, power law index was fixed to 1. This graph shows viscosity ratio on the horizontal axis and intrinsic viscosity on the vertical axis. For the symbol in the graph, circles indicate tangential motion and triangles indicate tumbling motion. When lambda is between 3 and 5, RBC exhibits tangential motion. And when lambda is between 5.5 and 7, RBC exhibits tumbling motion. The critical internal and external viscosity ratio is thought to be lambda is between 5 and 5.5. This is consistent with the results of previous studies. This graph shows viscosity contrast on the horizontal axis and the inclination angle and the tumbling frequency on the vertical axis, respectively. The inclination angle decreased with an increase in the viscosity ratio. The tumbling frequency decreased with an increase in the viscosity ratio. These are consistent with the result of previous studies. Next, we investigated with non-Newtonian plasma. Here, power law index was fixed to 0.9. This graph shows viscosity ratio on the horizontal axis and intrinsic viscosity on the vertical axis. When lambda is between 3 and 4.5, RBC exhibits time-dependent motion. And when lambda is between 5 and 7, RBC exhibits time-dependent motion. The critical internal external viscosity ratio is thought to be that lambda is between 4.5 and 5. Therefore, the critical internal external viscosity ratio decreases compared to that of the Newtonian fluid. This graph shows viscosity contrast on the horizontal axis and the intrinsic angle and time frequency on the vertical axis respectively. The inclination angle decreased with an increase in the viscosity ratio. And the transition to tumbling and the inclination angle approach to 5. We consider that as the inclination angle decreased, the membrane could no longer follow the flow, and the RBC changed to a rotating motion. Next, power law index was fixed to 1.1. This graph shows viscosity ratio on the horizontal axis and the intrinsic viscosity on the vertical axis. Within the scope of this study, tumbling motion continued to be exhibited even as the internal and external viscosity ratio increased. Critical internal and external viscosity ratio is expected to exist when lambda is less than 3. Therefore, it is important to investigate the presence or absence of critical internal and external viscosity ratio in the future by investigating when lambda less than 3. Finally, we conclude that we investigated the effect of non-Newtonian properties of plasma on the critical internal and external viscosity ratio, which is point of change of motion. When n equals to 0.9, which is shear-shaped fluid, the critical internal and external viscosity ratio decreased. Therefore, the trend was consistent with that of Newtonian. Also, when n equals to 1.1, which is shear-shaped fluid, it continued to show tumbling motion. Therefore, further investigation of changes in motion mode RBC is needed in the future. That is all my presentation. Thank you for listening.